Start at the bottom, not with a theory, not with a species name, just the floor. It's a small space. Low ceiling, uneven floor, walls that sweat. The air doesn't move down here, and neither does the temperature. Ice ages come and go on the surface. This room stays roughly the same year after year for hundreds of thousands of years. Hold on to that. It's the single most important physical fact about this place, and it's the least dramatic. Cold, dark, and boring is what fragile things need if they're going to survive. Underfoot there's red clay, hard as concrete in places, and a crust of calcite laid down drop by drop over a very long time. And packed into that clay are bones, not scattered thinly the way you'd expect in a cave, concentrated. Thousands of pieces of them jammed together in a deposit only a few square meters across. They're broken, but they're not chewed to nothing. They're mixed, but they're not worn smooth. Skulls sit next to finger bones. Ribs sit next to teeth. Nothing about the arrangement looks like the tidy layout of a cemetery, and nothing about it looks like a random dusting either. They're human. Or close enough to human that the word is worth arguing about, and people have argued about it for 30 years. Now look up. Directly overhead there's a hole in the ceiling. That's the shaft. It runs up about 13 meters, and it's the only way into this room. 13 meters is roughly 4 stories. Straight down, no ledges worth the name, into a chamber with no exit. Nobody climbs that without gear. Excavators go down on ropes in helmets, one at a time. Everything they bring back out has to come up the same way, hauled by hand, and that's the modern route with modern equipment. We don't know exactly what the shaft looked like 400,000 years ago. Caves change, roofs collapse, passages silt up, new holes open. But the geologists who have mapped the system say there's no sign of a second, easier entrance into this chamber. And getting to the top of the shaft isn't easy either. Today you reach it by crawling. The pit sits about half a kilometer from the mouth of the cave system that holds it, and roughly 30 meters below the surface of the hill. The route runs through big galleries, then tight squeezes, then one section you cross on your stomach, then a ramp, then the drop. It takes a fit person a good while, and it's completely dark the whole way. Anyone doing this before lamps existed would have needed fire, carried by hand through passages where you can't stand up. That's not an argument against people going down there. People do difficult things. It's a constraint, and constraints are what let you rule things out. That's the situation. A blind hole at the end of a long, awkward crawl inside a hill in northern Spain. The hill is the Sierra de Atapuerca near Burgos. It's a low limestone ridge riddled with cavities. The Spanish name for the pit is Cima de los Huesos, the pit of bones. It earned the name. Systematic digging started in 1984. Since then, the pit has produced just over 7,000 human fossils. That's more pre-modern human material than any other site on Earth. Not the most complete skeletons, the most pieces, because that's what the work actually is. Fragments come up, get washed, get sorted, and get refitted, sometimes years apart. The sediment can't be processed underground. It goes out in backpacks up the shaft, out through the crawl, then down to a river to be sieved. Every summer for decades. That's the unglamorous engine behind everything else in this episode. Somebody carried a sack of clay 4 stories up a rope so that a tooth the size of a match head wouldn't be lost. Out of that came skulls. 17 of them at last count, some nearly complete, plus jaws, teeth, spines, hands, feet. The human bones sit in a single clay unit. They're not spread through the sequence. They're concentrated in one layer, and that layer has been dated, redated, and argued over for 3 decades. We'll get to the argument. The number most people quote today is around 430,000 years. Sort the fragments by which bone they are and by which side of the body, and you get a minimum head count. At least 28 people. That's a floor, not a ceiling. It means the material can't come from fewer than 28 bodies. The real number could be higher. Now, the other thing in the deposit, animals. Almost all of the animal bone is bare. One species, an ancestor of the cave bear, in very large numbers, mixed right through the human material. Bears in a pit make sense. They den in caves through the winter. They're heavy, they're clumsy in the dark, and juveniles wander. A vertical hole in a cave floor is a bear trap that resets itself every year. There are other carnivores too: wolf, fox, lion, lynx. All animals that might follow a smell into a cave or chase something that did. What's barely there is everything else. There's no real accumulation of deer, horse, or the other animals people ate, and no hearths. That absence matters. This doesn't look like a place where anyone lived, cooked, or butchered, and there's one stone tool. Exactly one, reported from the bone layer in more than 40 years of digging. It's a handaxe of quartzite, reddish and veined, made from stone that wasn't the normal local choice. The excavators nicknamed it Excalibur. Under magnification, its working edge looks unused. No rounding, no polish, none of the damage a tool picks up from work. That's the observation. What it means is a separate question, and it's a fight we'll come back to. An unused axe can be an offering. It can also just be an axe somebody finished and never got round to using. That's it. That's the whole inventory. Thousands of human bones, a mountain of bare, and one beautiful, apparently unused axe. So here's the question this episode exists to answer. How did at least 28 people end up at the bottom of a hole with no easy way in and no way out? There are 3 explanations alive in the scientific literature. Not 1, 3. 1, they fell. The pit worked as a natural trap, the way it demonstrably did for bears, and people went in the same way. 2, they were washed in. Bodies or loose bones accumulated somewhere else in the cave, then water and mud moved them into the pit. 3, they were put there. Other people carried them through the cave and sent them down the shaft on purpose. Each of those makes different predictions about which bones survive, about their condition, about the animals lying next to them. Specialists disagree about which one wins, and they disagree in print. The excavation team argues that people put them there. Other researchers working from the same skeletal data published a direct challenge saying the natural explanations can't be ruled out yet. Both of those are serious positions held by serious people. Anyone who tells you this is settled is selling you the ending. We're going to test all 3 against what's actually in the ground, not pick the one that sounds best. Before the how, the who. And the bones are unusually good at answering that because there are so many of them. Teeth are the best clock a skeleton has. Enamel lays down in daily increments and roots grow on a schedule, so you can age these people fairly tightly. And when you do, the population comes out strange. Roughly half the material comes from adolescents, teenagers in the years when a modern human is finishing growing. Add the young adults and you've accounted for most of the pit. This is a deposit made almost entirely of people between about 15 and about 30. Now the absences. Infants under 2 aren't there at all. Children under 10 are rare enough to be conspicuous. That's not a recovery problem. The whole deposit gets sieved and bones the size of a fingernail come out of it. If babies were in there, they'd have been found. It's worth being honest about how much these counts have moved, though. An early study of the collection put the minimum at 32 individuals. The genetics papers work from at least 28. The excavation team's recent summary says 29. Those aren't contradictions so much as different methods and different moments, but they're a good reminder that even the head count here is a working estimate. At the other end, older adults are scarce too. The oldest individuals in the sample look like they were somewhere in their 40s. So the shape of this assemblage is a bulge in the middle, heavy on adolescents and young adults, thin at both ends. Males and females look roughly evenly represented. Whatever selected these people, it wasn't sex. That profile is the first real clue about the pit, and it cuts against the simplest story. A cave that quietly swallows the occasional victim over centuries should collect the vulnerable. The very young, the very old, the frail. That's the pattern natural traps usually leave, and it's roughly what the bears in this same pit look like. This one collected the people at the peak of their physical lives. That's an odd thing for a pitfall to do. Hold that. It'll matter when we test the 3 explanations. First, the other long argument about these people. What are they? In 1993, the team published 3 skulls from the pit and said something careful. These look like the start of the Neanderthal lineage. Careful because the face is where it shows. Big mid-face, forward-pulled nose, the brow ridge divided into 2 arches. Those are Neanderthal traits, and most of them cluster around chewing. The face got specialized before the rest of the skull did, but the back of the head is not Neanderthal. The brain is smaller than a Neanderthal's. The package is mixed. Mixed packages are exactly what evolution produces, and they're exactly what makes naming things a nightmare. For years, the default label was Homo heidelbergensis, a catch-all for Middle Pleistocene Europeans who weren't quite Neanderthals. That name has since become one of the loudest arguments in the field, and we'll come back to it properly because you can't settle it without the genetics. For now, hold the description the excavating team themselves prefer. These people are a sister group to the later Neanderthals, not Neanderthals, on the branch that leads to them before most of the traits arrived. And the whole argument was hostage to a date nobody could pin down. The published estimates swung wildly across 2 decades, a minimum of about 200,000 years, then beyond 350,000, then in one paper 600,000. Those weren't sloppy. They were different methods measuring different things in a cave where water moves minerals around and ruins clean assumptions. Newer luminescence dating and a model built on the layers themselves brought it back to somewhere around 430 to 450,000. Then genetics arrived, and it did something the bones couldn't do on their own. In 2013, a team recovered an almost complete mitochondrial genome from one thigh bone from the pit. Mitochondrial DNA sits outside the cell nucleus. There are lots of copies per cell, so it's the easiest ancient DNA to catch. The result made no sense. The Sima mitochondrial lineage looked closer to Denisovans than to Neanderthals. Denisovans are the eastern cousins of Neanderthals, known from Siberia. Finding their maternal signature in Spain was a genuine problem. But mitochondrial DNA follows only one line, mother to mother to mother, one thread out of thousands. To settle it, you need nuclear DNA. That's the real genome, the one that carries ancestry from everybody, and at this age it's close to impossible to get. Before this, the oldest hominin nuclear DNA anyone had recovered came from remains a fraction of this age. Much older DNA had been pulled out of permafrost, where the freezer never fails. Northern Spain is not permafrost. Here's why it's hard. DNA snaps apart continuously after death. After 400,000 years, the surviving pieces are shorter than a printed word. Almost everything in the extract is bacterial. The human fraction is a rounding error and it's chemically damaged. The Leipzig lab beat that with 3 moves. First, library preparation designed around single strands, which keeps the tiny, broken pieces that older methods threw away. Second, capture. You use synthetic bait matched to human sequence, and you fish the handful of human fragments out of an ocean of bacteria. Third, computing. Fragments that short match things by accident all the time, so a lot of the work is proving a match isn't luck. In 2016, that stack of techniques produced nuclear sequence from 2 specimens from the pit. Later work added a third. And the nuclear DNA came down clearly on the Neanderthal side. These people belong on the branch leading to Neanderthals, not to Denisovans, which resolves the paradox and dates something. If the Sima nuclear genome is already Neanderthal-leaning, then Neanderthals and Denisovans had already split before these people died. Then there are individuals. And here you have to be strict about 2 different things, what the bone shows and what you're allowed to conclude from it. One child's skull, cranium 14, has a suture that fused early on one side only. That's the observation, and it's rare in any population. The skull grew lopsided as a result. The inference people draw is heavier, that a child with a deformity like that survived years in a hunting society, which suggests it wasn't abandoned. That's plausible. It isn't proven by the bone because the bone can't tell you how the group behaved. Same discipline with the oldest individual in the collection. The lower spine is deformed and worn, and the person was past 45. Walking would have hurt. Everything past that is interpretation. And here's why the discipline matters. Another skull from the pit has bony growths in both ear canals. For years that was read as deafness and used as more evidence for care. Then someone remeasured the canals and modeled the acoustics and concluded the growths probably didn't affect this person's hearing much at all. Same bone, same site, same team. The claim just didn't survive contact with better measurement. One more case is different because the damage isn't wear or disease. It's a skull with 2 holes in the front of it, and it's the reason this pit is famous. Cranium 17. Here's where the short versions of this story cheat. They tell you there's a pit full of people, and then they tell you what it means. Everything between those two sentences is 40 years of work by a lot of people in the dark, and that work is where the evidence actually comes from. If you don't know how these bones came out of the ground, you can't judge a single argument about how they got in it. So start above ground and start with something that has nothing to do with archaeology. In 1896, a British registered company got permission to build a narrow-gauge mining railway across this part of northern Spain. The point was iron, ore and coal from the mountains to the south, hauled north to the foundries. 1,500 men worked on it. The line ran about 65 kilometers and it was finished in 1901. To get through the Sierra de Atapuerca, the engineers cut a trench along its southwestern flank. Half a kilometer long and at its deepest close to 20 meters, and that trench went straight through the middle of the hill's plumbing. Atapuerca is riddled with old caves that filled up with sediment and sealed themselves shut. From outside you'd never know. There's no opening, no hollow sound, just hill. The cutting sliced them open sideways. It turned buried caves into cliff faces you could walk up to and look at. Three of the most important sites at Atapuerca are just faces in that trench: the Elephant Pit, the Gallery, and the Great Sinkhole. The railway itself was a failure. By about 1910 it had stopped running, and the company behind it was gone by 1917. Then in 1950 somebody used the trench as a quarry and took out more of the deposits. So the record here is already damaged before anyone with a trowel arrives. That's normal. Industry finds most archaeology, and industry is not careful, but it worked. Fossil bone in the trench faces is what put Atapuerca on the map and what eventually put a research team on the mountain. Now, one thing that gets garbled constantly. The pit of bones is not in the railway trench, it's on the other side of the story. It sits deep inside a separate cave system you enter through a natural mouth and walk into, which means the trench didn't find it. People did on foot in the dark and long before any of this was science. The pit had a local reputation. It was the place you went to get a bear skull. From at least the early 1900s, cavers were going down that shaft and coming back up with bear fossils. Trophies, proof they'd made it. To get at them, they dug, not with a plan. They pulled bones out of the deposit and threw the spare dirt to one side. That dirt was full of human bone. Nobody knew, and a lot of it got broken doing it. In 1976, a doctoral student named Trinidad Torres came looking for bears for a thesis on bears. He came out with 17 human specimens. That's the moment the pit stopped being a bear cave. Systematic work started in 1984, and before anybody could excavate anything, they had to solve a logistics problem. Look at what you're dealing with. The chamber is around half a kilometer in from the cave mouth and about 30 meters under the hilltop. You crawl and squeeze to get there. You can't carry anything bulky because there are places where your own shoulders barely fit. Then the drop. The published figure for that shaft is about 13 meters, though the team's own papers have also put it at 15. Either way, you go down on rope. One person at a time, and everything you need goes down with you or comes down after you. At the bottom there's a ramp. It runs about 10 meters, it's between 2 and 3 meters wide, and it tips downhill. That ramp feeds the chamber where the bones are. The far end of it isn't bigger than about 20 square meters. Think about that as a workplace. It's roughly the floor area of a small bedroom with no door and no window. Only a handful of people can be in there at once, and they're working on their knees in each other's light. There's no daylight ever. So the first thing that went in back in the 80s was electric lighting run down the shaft, then scaffolding. Suspended decking over the deposit so people can reach the surface they're digging without standing on it. Now the part nobody puts in the documentary. Where does the dirt go? Every gram of sediment you remove has to leave the chamber. It gets bagged and it gets hauled up the shaft by hand. Then somebody puts it on their back and carries it out through the same crawl you came in by. Then it goes on a vehicle and down to the river. The sediment gets dried, then washed through screens at the Arlanzon. That's where the small things turn up, and small here means small. The collection includes the tiny bones at the ends of the toes. That's the loop. Dig a little, bag it, haul it, drive it, wash it, sort it, repeat for 4 decades, but the first 6 years weren't excavation at all. They were cleanup. Remember the trophy hunters? They'd left a mound of dug-over dirt sitting on top of the site. The Spanish team calls it the revuelto, the churn. Between 1984 and 1990, under Emiliano Aguirre, several tons of that disturbed sediment came out of the chamber. It wasn't empty. Around 600 human remains came out of the churn in those years, and here's the cost. Those 600 pieces arrived with no address. You've got the bone. You've lost where it was, what it was touching, and which layer it came from. That's gone permanently. You can still measure those fragments. You can still sequence them. What you can't do is use them as evidence about how the deposit formed, and the churn reached down into the top of the bone-bearing layer itself. The damage isn't a clean slice off the top. The team can spot revuelto material because it carries its own signature: scuffing, abrasion, the marks of being trodden on recently. By 1992, they were finally into deposit nobody had touched. That's when this becomes an excavation. And an excavation on a bone bed like this isn't really digging, it's recording. Digging is just how you get the next thing to record. The floor gets divided into a grid of squares. Everything that comes up belongs to a square before anything else is known about it. Then you go down in thin, controlled slices, spits. You take the whole square down a set depth evenly, and you don't chase the interesting bit. Before anything is lifted, its position gets fixed in 3 dimensions, 2 across the floor, 1 for depth. Which way it's pointing gets recorded too. A bone lying flat and a bone standing on end mean different things. This is the part people find hard to believe. The position matters more than the object. A finger bone on its own tells you almost nothing. A finger bone still sitting next to the right neighbor tells you the hand arrived here attached. 2 pieces of the same skull 3 meters apart tells you something else. So does the direction they're both lying in. Water moving through a cave sorts things. It lines long bones up. It carries light pieces further than heavy ones. A body that falls and rots in place scatters differently again in a pattern that follows the joints. You can only read any of that off the map. Pull the bone without mapping it, and the map for that spot is blank forever. Which brings us to the other half of the job, and it happens above ground years later. Almost nothing comes out of this pit hole. It comes out as pieces. So somebody has to work out which pieces belong together, and that process is called refitting. You take a fragment and you try its broken edges against every other fragment that could plausibly be from the same bone. Curvature, thickness, the pattern of the surface, and above all, whether the fracture lines actually run into each other. It is exactly as slow as it sounds, and it's how the famous skulls from this site exist at all. Take the skull that made this place famous, the one with the 2 holes in the front. That specimen is put together from 52 separate fragments. 52 pieces found across different squares over different summers by different people. None of them arrived labeled. The skull only exists because someone matched the breaks, and refitting isn't just repair work, it's evidence, and it's some of the strongest evidence at this site. Every successful join is a measurement. It says these 2 points in the chamber were once one bone, so the distance between them is the distance something moved. Do that hundreds of times and you get a picture of how much the deposit has been stirred and in which direction and over what scale. The spine gives you the same signal. Around 60 vertebrae from the pit have been rebuilt out of separate fragments, and some joins cross the worst boundary in the site. Pieces pulled out of the churned spoil have been refitted onto pieces still lying in place in the undisturbed layer below. That single fact does a lot of work. It says the trophy hunter's spoil heap came off the top of this deposit, not from somewhere else. It ties the orphaned material back to the site it lost. Now the pace, because this is the bit that gets skipped, and it's the reason the site is trustworthy. Atapuerca digs in summer. The season runs from around the middle of June to the end of July. That's it. 6 weeks or so once a year, and then the mountain closes. Across all the sites in the Sierra, roughly 300 specialists take part each year. Only a fraction of them are ever in the pit. Watch what that does to the numbers. By 2004, 20 years in, the collection stood at about 4,000 human specimens. Over the following 16 seasons, they recovered around 3,600 more. That's the shape of the work. Decades to build a sample, one short summer at a time, and they aren't finished. Less than half of the deposit has been excavated. The rest is still sitting there, mapped and waiting. It's worth being blunt about what that slowness buys you. It buys the map. A faster dig would have the same bones and none of the information, which is where this section hands over. All of that effort produces one thing: a record, positions, depths, orientations, which bones are present and which aren't. What the fracture edges look like, which fragment refits to which, and how far apart they were lying. 3 explanations are still standing for how those people got down there. They fell, they were washed in, or they were carried in and dropped. Every one of them has to explain that record, not the story. The record, that's the test, and that's what we run next. Here's the thing nobody warns you about caves. There's no date written in one anywhere. You can't look at a layer of clay and know how long it's been sitting there. Clay doesn't age visibly. It doesn't rust, it doesn't fade, and it doesn't tick. So when someone tells you these people died 430,000 years ago, the fair response is a question. How would anybody know that? Start with what's not being dated. The bones aren't being dated. Almost never at this age, bone is a sponge. Groundwater moves through it for hundreds of thousands of years, carrying dissolved minerals in and washing them back out. Every clock we're about to describe works by counting something that accumulated in a sealed box. Bone isn't a sealed box, it leaks both ways, so the work is indirect. You date the things around the bones and above them and under them, and you box the bones in. That's the whole game. Nobody dates the dead here, they date the dirt. Method 1, uranium series run on flowstone. Flowstone is the smooth mineral sheet that builds up where water runs over rock. It's calcite laid down in layers, drop by drop, year after year. Here's why that's useful. Water dissolves uranium out of the limestone and carries it along. Thorium doesn't dissolve, so it stays behind. So fresh calcite starts out with uranium in it and effectively no thorium. Then the uranium starts decaying and it makes thorium, and the thorium is stuck there. Measure the ratio between them and you've got a stopwatch. Lots of uranium and almost no thorium means young. A balanced mixture means old. That's the clean version. Now the catch, and it's the one that broke this site for 20 years. The stopwatch runs out. The thorium builds up fast at first, then slower, then it stops changing at all. Scientists call that equilibrium. Once a sample hits it, the method can't tell you anything except older than this. At Atapuerca, that ceiling sits somewhere past 350,000 years. There's a second limit, and it's geometry rather than chemistry. The crust formed after the deposit. It has to. It grew on the surface of something that was already there, so the age of the crust is a floor, not an answer. The bones underneath are older than the cap. How much older, the cap can't say. That phrase will come back, minimum age. The true number is somewhere above this, and nobody knows how far. Occasionally you get lucky. Sometimes carbonate grows directly onto a bone, and then the gap between the two is very small. Method 2. Electron spin resonance, run mostly on tooth enamel and on quartz grains. Everything buried in the ground sits in a faint bath of natural radiation. Uranium and thorium and potassium in the surrounding sediment, plus cosmic rays from above. That radiation knocks electrons loose inside crystals. In a good crystal, some of those electrons get stuck in flaws in the structure and stay stuck. They pile up. The longer something's been buried, the more trapped electrons it's carrying. Electron spin resonance counts them. You put the sample in a magnetic field, hit it with microwaves, and the trapped electrons answer back. What you get is a dose. How much radiation this crystal has absorbed since it was buried. To turn a dose into a date, you need one more number. How fast the radiation was arriving. Dose divided by rate gives years. And that's where it gets ugly, because the rate isn't constant. Water content changes it. Groundwater moving uranium around changes it. Enamel is decent at holding its signal, but it soaks up uranium from outside over time, so you have to model how fast it took that uranium on. Guess the uptake wrong and the age comes out wrong. That assumption is doing enormous work. On bone it's worse. Bone takes up uranium greedily and unevenly, which is why almost nobody trusts a straight bone date at this age anymore. Quartz is cleaner. It doesn't gain or lose uranium the way tissue does, so it's the preferred target now. Method 3, luminescence, and this one measures something genuinely different. Luminescence doesn't ask how old the mineral is. It asks when that grain last saw daylight. Same trapped electrons as before, but sunlight empties those traps. A grain lying on an open hillside gets wiped clean in hours. Then that grain washes into a cave, gets buried, and the light stops. From that moment, the traps start filling again, so the clock starts at burial. That's exactly the event you care about, which is why this method took over. Two flavors. Thermoluminescence heats the sample and counts the light that comes off as the traps release. Optically stimulated luminescence does it with light instead of heat, and it's gentler and more precise, which is why these labs run under dim red light. Open a sample in daylight and you've erased the thing you came to measure. Now the failure modes. First, saturation. The traps fill up. Once a crystal is full, more time adds nothing. Ordinary quartz saturates well short of 500,000 years, which is a problem because 500,000 years is precisely where this site lives. The fix was to find slower signals, deeper traps in quartz that fill more gradually, and a signal in feldspar that fades less. These are the extended range methods. They push the usable window back far enough to reach this deposit at all. Second, failure mode. If a grain never really saw the sun on its way in, its clock was never reset and it'll read too old. That's why the newest work measures grains one at a time. If a few are lying, you spot them as outliers instead of averaging them in. Then the cross-checks. The two of them, and neither gives you a date on its own. Magnetism first. Some clay minerals settle out of water lined up with the Earth's magnetic field, and then they're locked that way. The field flips, not on a schedule, but the last big reversal is dated, and it's roughly 780,000 years back. The clay in the pit reads normal, same polarity as today. So the deposit is younger than that reversal. It's a ceiling, not a date, but a ceiling that rules out a whole category of wrong answers is worth having. The other cross-check is the animals. Voles and mice mostly, because their teeth change shape fast on geological timescales. Find a species known to appear and vanish inside a dated window elsewhere, and you can slot your layer into a sequence. That won't give you a number. It'll tell you if your number is absurd. Now the history. Because all of these were applied here in order over 30 years and they didn't agree. 1997. The first serious geology and dating paper on the pit, led by James Biscoff. They dated the flowstone that caps the whole deposit. It came out young. It formed between about 68,000 and about 25,000 years ago, which tells you nothing except that the cave was still active recently. So they went at the bones themselves and at broken pieces of older speleothem mixed into the mud. The bone dates came back scattered and soft. Uranium series on bare bone gave 154,000, give or take 66. On human bone, 148,000, give or take 34. Those error bars are the sound of a method struggling. Electron spin resonance on bare bone gave 189,000, give or take 28. Combining the two methods on selected samples produced 200,000, give or take 4. That's the number that entered the literature. A firm minimum of roughly 200,000 years for people entering the pit. But read the same paper carefully and the authors are already uneasy. One combined sample came out at 320,000, and the broken speleothem in the mud was at equilibrium, meaning older than about 350,000. The minimum was defensible. It was also obviously incomplete. 2003. Same lead author, better instruments, and a title that says the quiet part out loud. Beyond equilibrium, greater than 350,000 and perhaps 400 to 500,000. 2007. Higher resolution again, and the number jumps to 600,000. The error range on that one is worth hearing in full. Minus 66,000 plus infinity, meaning at least this old, and there's no upper bound the method can supply. 2014 is where it settles. Lee Arnold and colleagues went after the sediment sitting directly on top of the bone bed using the extended range luminescence signals. Feldspar gave 433,000, give or take 15. Quartz gave 416,000, give or take 19. 6 separate samples, all reproducible, combining to a minimum age of 427,000, give or take 12. The same year, Arsweja and a very long list of co-authors published the 17 skulls and put the layer at around 430,000. Part of that rested on uranium series dating of carbonate that had grown directly onto a skull. But notice what everything so far had in common. It was all from above, a minimum again. 2019 closed the other end. Martina de Muro and colleagues dated the red clay that holds the bones and the clay underneath it, grain by grain. 4 ages came out, clustered between about 437 and about 460,000, with error bars between 38 and 56,000. Then they fed those into a model of the layer sequence. It brackets the bone-bearing unit between 455,000, give or take 17, and 440,000, give or take 15. Main, 448,000, give or take 15. That places these people in the glacial stage geologists number 12, which runs roughly from 478 to 424,000 years ago. A cold world, so. 400,000 years of spread between the lowest published figure and the highest. Does that mean the science is unreliable? No. And it's worth being precise about why not. The 97 team wasn't careless. They used the best methods anyone had on the only material they could get, and they said out loud that their clock topped out. Their problem was that bone leaks and uranium series runs out. Every figure after that came from a method that didn't exist or didn't work when the previous one was published. And every one of those papers stated its own limits in the abstract, minimum, perhaps, plus infinity. That's not a field covering itself, that's a field showing its work. So here's the number the rest of this episode is built on. These people went into the pit somewhere around 430 to 450,000 years ago. The best current estimate is 448,000, give or take 15. 15,000 years of slack in either direction, and that's the good version. It took 3 decades of argument to get the uncertainty down to something that small. Cranium-17 can wait a few minutes. Take the whole deposit first. Because a skull with 2 holes in it tells you about one person. The question is about all of them, and it has to be answered with the whole assemblage or not at all. The field that answers it is taphonomy. Everything that happens to a body between death and the day somebody digs it up. Taphonomy asks boring questions on purpose. Which bones are here and which aren't? Are they broken, and broken how? Did anything chew them? Did anything move them? Each of the three explanations makes different predictions about those answers, so you don't argue about the story, you argue about the bones. Explanation 1, they fell. This one has the strongest thing any hypothesis can have. A demonstrated example. The pit did work as a trap. It's full of bears. Bears den in caves. They're heavy, they're half asleep in winter, and juveniles wander. The pit caught them for a very long time, so the mechanism isn't hypothetical. It's sitting right there in the same clay as the people, and people fall. Caves are dangerous now with helmets and rope. They were worse then. Here's what strains it. Start with who's in the deposit. A trap that swallows the occasional victim over centuries, collects the weak, the very young, the very old, the sick. That's roughly what the bears in this pit look like. The people don't. This deposit is adolescents and prime adults, with infants under 2 missing entirely. That is not what accidents produce. Then there's the geography. To fall into this shaft, you first have to be standing next to it. That means half a kilometer of cave in the dark, ending at a dead-end pit. Bears had a reason to be in there. People didn't, as far as anything in the deposit shows, but that argument has a hole in it, and the excavators are honest about it. We don't know what the roof looked like then. 2 chimneys in the wider system may have been open to the surface at the time. If one was, the walk gets a lot shorter, and falling gets a lot easier. Nobody has settled that question, and it's the single loosest board in the floor. Explanation 2. Nobody carried anything and nobody fell in. The cave moved them. This is the one that gets treated as the boring option, and it is the one with the sharpest published case behind it. Start with the sediment itself. The layer holding the people is described in the dating papers as a clay breccia. Breccia means broken material that got moved and dumped, not material that settled quietly where it lay. So something in that chamber flowed. Mud, water, gravity over an unknown span of time. That's not a fringe reading. It's the standard description of the deposit. In 2018, a team led by Charles Egeland pushed that much harder in the proceedings of the National Academy of Sciences. Their method was simple to state. Take the count of which skeletal parts survive. Feed it to a battery of machine learning classifiers. Ask which known assemblage the pattern resembles. They ran it against 14 comparison sets across 8 categories. Real burials, bodies left on the surface, bodies scavenged, baboons killed by leopards, baboons that just died in caves. Sima didn't land with the burials. It landed with the scavenged and the naturally accumulated. The pattern driving that is the missing material. Spine and rib elements are scarce, so are the spongy ends of the limb bones and the small bones of the hands and feet. All of it is the light, soft, chewable end of a skeleton. All of it is what carnivores take first, then the tooth marks. The excavation team reported them on under 4% of the collection. Egeland's group argued that ancient chewing had been misread as later cracking. Correct for that, they said, and the figure roughly doubles. On the thigh bones specifically, it climbs toward a third. If that's right, something was eating these bodies, not once, routinely. Their conclusion is worth stating in their own terms. Non-anthropogenic agents and abiotic processes cannot yet be ruled out as significant contributors, and they were careful about the other half. Their result doesn't falsify deliberate deposition. It says the same numbers also fit a natural history, where it strains is the source. Water moves bones from somewhere to somewhere. Nobody has produced the somewhere. There's no upstream chamber full of the people who didn't make the trip, and a blind room at the bottom of a shaft isn't an obvious catchment for a river. The excavation team also reads the same collection the other way. Their 2024 assessment concludes carnivores, probably bears, had limited access and that complete bodies were probably placed in the site. Which brings us to explanation 3. Somebody carried them in. The case is mostly made of absences, and absences are weaker than evidence, but there are a lot of them and they point one way. No hearths, no butchered game, no debris of living. Whatever this chamber was, nobody used it, which makes an accidental human presence at the lip harder to picture. One stone tool in 40 years of digging and its edge looks unworked. That's either an offering or a coincidence, and one object can't tell you which. And the age profile. A deposit of healthy young adults is what you get from a population sample, not from a hazard. Which is the point where cranium 17 stops waiting. 2 fractures on the left forehead. Neither one healed, so both happened at or very near the time of death. In 2015, Nohemi Sala's group published the measurements. The two are close to the same shape and close to the same size. Their argument runs on that similarity. Same shape, same size, most likely the same object. But the two sit at different angles and the force came in along different lines. That combination is the whole case. One object, 2 separate contacts from 2 directions. A fall is a poor fit for that. A body dropping 13 meters usually meets the floor once in one direction against whatever the floor happens to be. Getting a second, matching contact out of the same drop takes a coincidence nobody has managed to model. So Sala's team read it as violence and called it the oldest case of lethal interpersonal violence in the human record. Their line is that repeated blows imply intent. Now be strict about what that buys you. If they're right, this person was dead or nearly before reaching the bottom, which means at least one body got into that chamber because a person put it there. That's an anthropic entry confirmed for one individual. 1 out of at least 28. It says nothing about the rest, and Sala's team doesn't claim it does. It also doesn't tell you why. A body carried in and set down carefully, and a body pushed over an edge to be rid of it, leave the same skull. If anything, a killing argues for disposal at least as easily as for ceremony. Concealment is a motive too. And the reasoning rests on 2 marks on 1 bone out of 17 crania. It's a careful argument. It is not a large sample. So here's where section 3 ends, and it doesn't end tidily. 3 explanations, none of them eliminated, and they aren't exclusive. Real deposits are usually mixtures. Some fell, some were placed, and the cave rearranged whatever it got. Let's take the 3rd explanation seriously for a minute, not accept it. Just run it and see what it costs. Suppose people carried bodies to that shaft. What does that actually require of them? Start with the physical bill. half a kilometer underground through galleries, then squeezes, then a stretch you cross on your stomach, in complete darkness, which means fire carried, kept alive in passages where you can't stand up. A dead adult is dead weight and awkward. That's not a one-person job through a crawl. It's several people coordinating for hours, and none of it feeds anybody. There's no calorie return on this trip. Whatever the reason was, it wasn't hunger. So the minimum you're buying is this: a shared decision that a body should go somewhere specific, and a group willing to spend a day getting it there. That's a real claim about minds 430,000 years ago. It's also much smaller than the claim people usually make from it, and there's a prior question nobody can answer. Was this one event or a habit? The bones sit in one layer. A layer doesn't come with a stopwatch. 28 people could have arrived in a season or across 1,000 years, and the clay would look about the same. That matters enormously. A single disaster and a tradition kept up for generations are completely different claims about a mind. The site doesn't currently distinguish them. Here's the line that matters: putting bodies somewhere is not the same as believing in an afterlife. The behavior has ordinary explanations that cost nothing cognitively. A body in the camp smells. It draws scavengers, and scavengers are a problem you don't want at home. It also upsets the living. Every one of those reasons produces exactly the same archaeology as reverence does, and we're not the only animals that react to our dead. Chimpanzee mothers carry dead infants for days. Elephants stop at bones and handle them. None of that is religion, it's attention. And the gap between attention and belief is exactly where most popular writing about this site quietly cheats. The pit shows behavior. It doesn't show belief, and no amount of digging is going to turn up a belief. The word burial doesn't fit either. Nothing was dug. Nothing was covered on purpose as far as anyone can demonstrate, which is why the genetics matter so much. It's the one line of evidence in this story that came back with a hard answer. Recap the problem. The maternal DNA from the pit pointed east toward Denisovans. The bones pointed toward Neanderthals. Those can't both be the whole story. Nuclear DNA broke the tie. 2 specimens in 2016, a third later, and all of them land on the Neanderthal branch, which is the answer the skulls had been giving since 1993, arrived at by a completely independent route. That's about as good as agreement gets in this field. Now follow what it does to the calendar. If these people are already leaning Neanderthal, then the Neanderthal and Denisovan lines had already parted before they died. So that split has to be older than the fossils, older than 430,000 years on the published reading. And the branch separating all of them from our own lineage sits below that one, so it's older still. The whole tree got pushed back. The mitochondrial oddity didn't go away, though. One specimen's maternal line still looks Denisovan. The proposed fix is that later Neanderthals swapped their maternal lineage out. A new population moved in and its mother's line replaced the old one. That's a genuinely useful lesson, and it's bigger than this cave. One gene's history is not a population's history. There's a second thing: the DNA changed, and it's practical. This is a temperate cave in Spain, not permafrost. Sequence that old had been coming out of frozen ground. Getting it out of a Spanish hillside moved the boundary of what people even bother attempting. Now the wider damage the site did to the field, which is mostly damage to a tidy story. Before Sima, Middle Pleistocene Europe was a scatter of single finds, a jaw here, a face there, decades and hundreds of miles apart. With one specimen per site, you can't separate two things. Is a difference between species, or is it just two people who looked different? Sima answered that by brute force. Thousands of pieces from one chamber, from one narrow slice of time. That's not a data point, that's a distribution. And once you can see the spread, you can tell which traits are shared across the group and which belong to one person. That's how the mosaic showed up, and it's the sort of thing you simply cannot see with a sample of one. The Neanderthal face arrives early. The Neanderthal brain size doesn't. Features don't travel as a set. They arrive one at a time, over hundreds of thousands of years. That finding did real damage to the neat version of Homo heidelbergensis. A single ancestral European species gets much harder to defend when you can watch traits arriving separately. It also gave the Neanderthal lineage a dated floor. By the time these people died, the face was already recognizably on its way, though even that floor is a range, not a number. Depending on which method and which layer, you get something around 430,000 years, or closer to 450. So where does the argument actually stand? The excavation team publishes the anthropic reading, and their most recent taphonomy backs it. The 2018 challenge hasn't been withdrawn, and nobody has published a result that closes it. Two careful groups, one collection, two readings. Neither side is being unreasonable, and that's the tell. When good people can't agree on a data set, the data set usually isn't finished yet. So let's be concrete about what would settle it, because that's the honest part. 1. A second chamber of the same age with a known cause to compare against. Right now the pit gets measured against baboons and modern forensic cases because there isn't anything closer. 2. Bones still joined the way they were in life. If any individual turns up in anatomical order, water transport becomes very hard to argue. 3. A firm answer on the roof. Whether anything overhead was open to daylight when these people arrived is still unresolved, and it decides how easy falling was. 4. More ground. The whole symbolic argument lays on a single stone tool, and one object is a sample of one. Either more turn up, or 40 years of nothing becomes a real number instead of an anecdote. 5. Work on the drop itself. Nobody has modeled a 13-meter fall in this specific shaft well enough to say what it does and doesn't leave on a skull. Until somebody does, the fall hypothesis is being ruled out mostly by intuition. None of those 5 have arrived. That's not a failure of the site. It's what a hard question looks like while it's still open. So the honest ending isn't a verdict. It's a sack of clay going up a rope, the way one has gone up that rope every summer for 40 years. The answer, if there is one, is in that sack, or the next one. Somebody will wash it out in a river, and it'll be the size of a fingernail. That's what a first actually is, not a moment somebody lived through. A claim sitting in a bucket, waiting for the argument to catch up with it. Go back to the femur for a minute. The strangest thing about this site isn't the skulls or the shaft or the axe, it's that anybody got DNA out of it at all. On the chemistry as it was understood, that shouldn't have worked. Here's the problem. A living cell spends energy every second keeping its own DNA intact. A crew of repair enzymes patrols the molecule, fixing damage as fast as it appears. When you die, that crew clocks off. The damage keeps happening and nothing fixes it. And the first wave comes from inside. Your own enzymes, the ones normally locked away in compartments, spill out and start cutting. Then the bacteria arrive. Decay is mostly other organisms eating you, and they eat DNA along with everything else. If anything survives that, it's down to water and air, and they work slowly. That's where the real clock starts. Water attacks the molecule in two ways that matter. The first is called depurination. A water molecule knocks one of the letters clean off the backbone. That leaves a hole, and a backbone with a hole in it breaks there. That's how long DNA turns into short DNA, and it never runs backwards. The second is deamination. Water strips a chemical group off one of the four letters, cytosine, and turns it into something a sequencer will read as a different letter. Hold on to that one. It looks like vandalism. It's the most useful thing in the field. Oxygen does its own damage on top of that, scarring individual letters so badly that a sequencing enzyme just stops when it hits one. Those are the three processes. Cutting, miscoding, and blocking. All of them speed up when it's warm, and all of them need water. Which is why the worst place to leave a body if you want its DNA read later is warm, wet ground. Warm drives the chemistry. Wet supplies the reagent. Add soil bacteria and you've built a machine for erasing genomes. So how long does it last? For years, the honest answer was an extrapolation, and it was gloomy. Lab measurements of the chemistry projected forward said DNA shouldn't survive more than a few 100,000 years anywhere. Then in 2012, a team got a real number out of real bones. They measured DNA in 158 radiocarbon-dated Moa bones from New Zealand, all from one small area, so burial conditions were roughly matched. They got a half-life. At an effective burial temperature of about 13 degrees, a 242 base fragment halved every 521 years. Then they projected it. At 15 degrees, a 30 base fragment halves every 3,000 years, and the average molecule is down to a single base after about 130,000. Drop it to 5 degrees and you buy a lot. The half-life goes to 20,000 years, and the average molecule lasts something like 880,000. Those are model numbers, and the authors said so. The model leaves out the fast first phase of decay, but the shape was clear and it matched where records were actually being set. Frozen ground. 6 months before the CIMA result, a team published a draft genome from a horse bone out of permafrost. That bone was dated to between 560 and 780,000 years old. That was the oldest genome anyone had by almost a factor of 10. It came from ground that had never thawed. Northern Spain is not that. It's a temperate hill in a country with hot summers. Nobody was drawing up plans to break the record there. Except 30 meters down, the hill stops being Spain. Go far enough in and the surface stops reaching you. Summer doesn't arrive. Winter doesn't either. The rock averages everything out. The chamber at the bottom of that shaft sits at a constant 10.6 degrees Celsius. Humidity is close to saturation. Note what that isn't. It isn't dry. There's water everywhere down there, and water is what breaks the molecule. So the cold is doing the work, not the dryness. And the deposit sat undisturbed. No wetting and drying, no roots, no annual freeze and thaw, and there was already a clue. Before anybody touched the human bones, a complete mitochondrial genome came out of a cave bear from this same chamber. Molecular dating put that bear at roughly 409,000 years old. The site preserved. Now be careful about what that establishes. The temperature and the humidity are measurements taken today. That the chamber held that temperature for 400,000 years is an inference. A good one from how deep caves behave, but an inference. And nobody can say exactly why these bones kept DNA when plenty of cool caves give up nothing. Preservation varies from bone to bone inside a single layer. The honest version is that this site was unusually good and not fully explained. Which brings us to the part that eats most of the effort, not the sequencing. Keeping your own DNA out of the answer. Here's the trap, and it's specific to humans. Sequence a mammoth, and anything human in the tube is obviously not mammoth. You bin it. Sequence a human fossil, and the contamination is human too. Sorting by species tells you nothing, and the ratio is brutal. In most of the extracts from this femur, fewer than one sequence in 1,000 matched the human genome at all. The rest was bacteria. Against that, a single skin cell from a person handling the bone contains a complete, undamaged, modern genome. It doesn't take a sneeze. A fingerprint is plenty. They found exactly that. The samples richest in human DNA were the ones taken from the femur's outer surface. Up to 8% against 0.1% inside the bone. That's not the ancient individual, that's everybody who ever picked it up. So the physical protocol is defensive. Strip about 1 millimeter of surface off before you sample. Drill slowly around 1,000 revolutions a minute because friction heat destroys what's left. The room is defensive too. Clean labs run at positive pressure, so filtered air pushes outward and nothing drifts in. Surfaces get bleached and ultraviolet lights run overnight. People come in covered, suit, hood, mask, 2 pairs of gloves. And amplified DNA from finished experiments never comes through the door because one droplet of that would swamp everything. Then you run blanks, empty tubes carried through every step alongside the samples, so whatever the lab itself contributes shows up in a control. None of that is enough. Some contamination always gets through. So the real defense is in the data, and it rests on 2 things a modern molecule can't fake. First, length. All that hydrolysis chops ancient DNA short and nothing puts it back. In this sample, the fragments piled up around 30 bases long, 30 letters. Modern contamination arrives intact and long. So the long sequences in the tube are mostly not your fossil. The team threw out everything above 45 bases. Second, the damage signature, and this is the elegant part. Remember deamination, where water turns cytosine into a letter the sequencer misreads. It runs far faster at the frayed ends of an old fragment than in the middle. So an ancient molecule carries a fingerprint. Misread letters piled up at the tips in one direction only. It builds with age, and fresh DNA off a technician's hand has no reason to show it. So you test for it, take only the fragments that show the damage at one end, then ask how often the other end shows it too. In this femur, the answer came back 55% and 62%. That's an old population of molecules. Libraries under 5% were declared too contaminated and dropped. Some of those were the ones with the most human DNA in them. That's the machinery. Here's what it produced in order. They took just under 2 grams of powder from one thigh bone, drilled at the natural breaks so the surface was never cut. That went into 77 separate sequencing libraries. Then they enriched for mitochondrial DNA using probes built from a modern human sequence. When the early reads came back looking Denisovan, they made fresh probes from the Denisovan sequence and ran it again. The result, published in December 2013, was about 98% of the mitochondrial genome, each position read about 30 times over. They could even date the individual from the sequence itself, because an old molecule has had less time to accumulate change. Point estimates landed near 400,000 years, with a range from 150,000 to 640,000. Wide, but the right order of magnitude. And the tree came out wrong. This maternal line grouped with Denisovans to the exclusion of Neanderthals at maximum statistical support. Be precise about what that did and didn't say. It did not say these people were Denisovans. It said one molecule, inherited down one line, sat on the Denisovan branch. The nuclear answer took 2 more years, and it came from an incisor and a piece of femur. It was published in March 2016, and it is barely data. They recovered less than 1,000th of the genome from each specimen. You can't read a genome like that, you can only count, so they counted matches. At positions where a known Neanderthal genome and a known Denisovan genome differ, which one do these fragments agree with more often? The answer was Neanderthal on both specimens. In 2018, a 4th specimen, a molar, joined them, using a method that measures how often ultra-short fragments land in the wrong place by chance. So why did the 2 molecules disagree? Because mitochondrial DNA is one locus with one history. The nuclear genome is thousands of histories inherited from everybody. 2 explanations survive. Deep lineages can sort unevenly by chance. Or Neanderthals later replaced their maternal line when a population carrying different mothers moved in. That second one gained support in 2017. A Neanderthal from Germany carries a maternal branch that split from other Neanderthals about 270,000 years ago. That's a floor for when a turnover could have happened. The general lesson outlived the argument. Read one molecule and you get that molecule's tree. That is not automatically the population's tree, and for years mitochondrial DNA was all anyone could get, so what got settled? These people sit on the Neanderthal side of the Neanderthal-Denisovan divide. That's the claim the data supports, and it's narrower than saying they were Neanderthals. It also puts a floor under the calendar. If the 2 lineages were already separate here, they split before these people died. Now the honest version of the number, because this is where popular accounts go wrong. Genome-based estimates put the Neanderthal-Denisovan split somewhere between 380,000 and 470,000 years ago. But that assumes one mutation rate. Assume the older rate and the same data give something closer to 200,000, which the Spanish fossils rule out because they're older than that. That's the real contribution, not a date. A constraint that eliminates part of the range, and then the limit. A genome tells you who a person was related to. That's the entire list. It doesn't say why they were in a cave. It doesn't say whether they walked in, fell in, or were carried. At least 28 people are at the bottom of a hole. And the most technically remarkable evidence at this site has nothing whatsoever to say about how they got there. So the genome says these people sit on the Neanderthal branch, which raises a question that sounds like housekeeping and isn't. What do you call them? For decades, the answer in the textbooks was Homo heidelbergensis. That name is now one of the most contested labels in the field. And the fight over it is worth your time because it shows you what a species name actually is. It isn't a fact about the world, it's a claim, and claims can fail. Start with the ordinary case. With living animals, a species is at least anchored to something you can watch. Two populations either interbreed and produce fertile young, or they don't. It's messy, with plenty of exceptions. But it's a test you can run. Now try running it on a jaw that's been in the ground for hundreds of thousands of years. You can't breed fossils, so the test gets replaced by shape. How different does a bone have to be before you call it a different kind of animal? There's no threshold. Living species vary enormously inside themselves. Male and female, young and old, one valley and the next. So every fossil species name is a bet. The bet is that the differences you're looking at are bigger than the differences inside one population. Here's the part almost nobody outside the field knows. A species name isn't attached to a description, it's attached to an object. The rules of zoological naming require a name-bearing type, one physical specimen in a collection that the name is nailed to permanently. That specimen doesn't have to be typical, it doesn't have to be complete. It just has to be the thing the name points at, which means that from then on, every question about the name is really a question about that object. Does this new fossil belong with that one? That's the whole test. So, the object. In 1907, in a commercial sand pit outside a village called Mauer, southeast of Heidelberg, a workman digging for sand hit a bone about 24 meters down. It was a lower jaw, massive, thick through the body, no chin at all. But the teeth in it were small, human-looking teeth in a jaw that looked nothing like ours. The following year, a Heidelberg scholar named Otto Schotensack published a monograph on it and gave it a species. Homo heidelbergensis. Now be very clear about what he had. A jaw, that's it. No skull, no face, no brain case, nothing below the neck. A mandible tells you real things. Tooth size, tooth shape, how thick the bone is, how the chewing muscles attached, whether there's a chin. It tells you nothing about brain size. Nothing about the brow ridge, nothing about the shape of the back of the head. Hold that thought because it's the whole problem. The Neanderthal traits at the pit are concentrated in the face and the front of the vault. Mauer preserves neither. Set the pit's date against the jaws. Mauer was redated in 2010 and it came out at 609,000 give or take 40. That's a long way older than the people in the shaft, so the type specimen is much older than these people from another part of Europe, and it's one bone. That's the object the name is nailed to. Everything after this is people arguing about what else belongs with it. For most of the 20th century, the name barely got used. Then it came back late in the century as a solution to a filing problem. Middle Pleistocene Europe and Africa were full of fossils that weren't Homo erectus, weren't Neanderthals, and weren't us. They needed a box. Heidelbergensis was the empty box with a valid name on it. By the early 2000s, the Sima crania were being placed in that box in print, alongside fossils from France and from Ethiopia, as one widespread ancestral species. The excavation team never quite bought the wide version. Their 1997 study of the crania said the European Middle Pleistocene fossils belong to the Neanderthal lineage, and none of them sit on a shared ancestor with us. So the same name was carrying two incompatible claims. A wide one spanning two continents, ancestral to everybody, and a narrow one, European only, ancestral to Neanderthals. Then the position moved, and it's worth saying plainly that it moved. Around 2012 and 2014, both camps converged on taking Sima out. The reason was in the faces. Once 17 crania were on the table, the Neanderthal features weren't a hint anymore. They were a pattern. When the team finally compared their whole jaw sample against Mauer directly, they reported something blunt. There's no counterpart of Mauer in the Sima collection. Read that carefully. The type specimen doesn't match the fossils that were being named after it. And then the genome landed on top of all this and made it worse, because the wide version of Heidelbergensis had a job. It was supposed to be the shared ancestor, the population that split into Neanderthals on one side and us on the other. The nuclear DNA says these people are already past that fork. They're on the Neanderthal side of it, so they can't be the ancestor of both. And the jaw in Germany can't help you because nobody's published a genome from it. It's shape or nothing. Which leaves the field with three moves, and it's currently making all three at once. 1. Restrict the name, keep Heidelbergensis, but only for Mauer and things that genuinely look like Mauer. That's a small European group and Sima isn't in it. 2. Redefine the neighbor, widen Homo neanderthalensis to take in Middle Pleistocene fossils that already carry Neanderthal features. Sima becomes early Neanderthals. 3. Drop it. A 2022 proposal argued Heidelbergensis is too poorly and variably defined to keep in either version and should be abandoned outright. That proposal got a hard answer. Names are governed by a code, and the code doesn't let you retire one because it's been used sloppily. The replacement it offered was rejected as a synonym with no value from the day it was coined. So watch the words people actually use now, because each one is a different assertion. Pre-Neanderthal says, inside the branch before the full package arrived. It puts them on the road without claiming they'd got there. Early Neanderthal says something stronger, that the species line should be drawn below these people, not above them. That's not a discovery. That's a decision about where to cut a lineage that never stopped changing. And Homo sp. Says the quiet part, genus, and nothing further. It's what you write when the honest answer is that you don't know yet. Here's where that leaves the pit. Those crania came up a rope out of a hole in the ground, and they've been in the same cabinets ever since. Same foam cutouts, same specimen numbers inked on the same bone. Nobody has recarved them. What changed is the sentence written on the card next to them, and it changed twice. First, they got called Homo heidelbergensis. Then they got taken back out of it. Now climb out of the shaft, walk back through the crawl, and stand on the hill. Because the pit isn't the site. The pit is one room in it. There's a trench cut clean through this hill. Straight sides, gravel underfoot, walls of rock and packed sediment rising well over your head. It isn't natural. This is the mining cutting from earlier, the one the railway company drove straight through the ridge and then walked away from. Stand in it now, and the failure is the least interesting thing about it. What they left behind is the reason any of this is known. The cutting sliced through the middle of the hill, and the hill was full of old caves. Those caves had filled up, sealed over, and gone quiet. The trench opened them in cross-section like a cake sliced through the tin. 3 of the major sites here are holes in the side of that cutting. They aren't caves you walk into. They're the fossilized insides of caves hanging in a wall. And they aren't the same age. That's the whole point of this place, and it's the thing that makes it different from almost every other site in the story. Start at the bottom of the calendar, the site called Cima del Elefante. The lower levels here are the oldest human evidence anyone has found in Western Europe. In 2007, the team pulled a piece of jaw out of level 9. A tooth still in it, not much to look at. It was dated by 3 independent roots: the magnetic record in the sediment, cosmic ray isotopes in the buried quartz, and the rodents. Rodents are the quiet workhorse of this. Small mammal species turn over fast, so the mix of voles in a layer is a clock. All 3 agreed on roughly 1.2 million years, and it wasn't alone. The same levels gave up simple stone flakes and cores and animal bones with marks on them from stone tools. Then in 2022, the same site produced something better: most of the middle of a face, cheekbone, upper jaw, the edge of the nose. It came from level 7, deeper and older than the mandible. Published in 2025, dated to between 1.4 and 1.1 million years ago. And watch how carefully the authors named it. Homo, followed by a Latin abbreviation that means roughly close to Homo affinis erectus. It's a placeholder wearing a species name. It says this looks like the erectus group and we are not committing further. That caution is doing real work. The face is flat and heavy in a primitive way. It doesn't match the later face from the site next door. Which brings us to that site, Grandolina, further along the same cutting and a lot younger. Grandolina is a stack, roughly 11 layers of fill, one on top of another, covering a long stretch of time. The famous one is layer 6. The excavators call it the Aurora Stratum, and it's the layer that made this hill's name. It has produced about 170 human specimens. 26 teeth and 144 bones. Sorted out, that's a minimum of 11 individuals, mostly children and adolescents, alongside them over 1,000 pieces of worked stone. Simple stuff, cores, flakes, no handaxes. The age comes from the Earth's magnetic field. It flipped globally about 780,000 years ago. That flip is recorded in the layer above. So layer 6 is older than 780,000 years. That part isn't controversial. How much older is. Luminescence work has pushed the lowest human material toward 900,000. Other estimates sit closer to 8. In 1997, the team gave the layer 6 people a new species name, Homo antecessor, and they made a very large claim in the paper's title. This, they suggested, might be the last common ancestor of Neanderthals and ourselves. The reason was the face. It's flat and hollowed under the cheekbone, and that's a modern-looking arrangement. Nothing that old should have a face like that. It looked like the ancestor everybody had been drawing on whiteboards. 23 years later, that claim got tested by a method nobody had in 1997. DNA is long gone at this age, but the proteins locked inside tooth enamel are tougher, and they carry a faint version of the same signal. In 2020, a team read the enamel proteins from one antecessor molar. The result moved it off the trunk. Antecessor came out as a close sister lineage to us, the Neanderthals and the Denisovans, beside the group, not below it, which flips the meaning of that modern-looking face. If antecessor isn't our ancestor, then a face like ours is older and more widespread than anyone assumed, and the Neanderthal face is the specialized one. There's one more thing about layer 6, and it needs handling carefully rather than dramatically. The human bones from that layer carry marks, short grooves, deliberate looking in specific places. Here's how a specialist tells a stone edge from a tooth. A cutting edge leaves a narrow groove with a V-shaped floor and usually fine parallel scratches running along inside it. A carnivore leaves rounded pits and smooth-floored scores. Different shape, different edges, no internal striations. The trampling makes its own confusion. Those marks are shallow, wander and sit on the high points where grit gets dragged. So you look at cross-section, at direction, at where on the bone it sits, and at what else is on the same piece. On these bones, there's more than grooves. There's percussion damage of the kind a hammerstone makes. There's a bending fracture the analysts call piling, which happens to fresh bone and not to dry bone. And the comparison that carries the argument is the deer. In the same layer, deer bones and human bones show the same processing, and they were thrown away in the same place, mixed together. The 1999 study that laid this out concluded the assemblage was purely consumptive. No sign of ritual, no sign of special treatment. That reading has been challenged from inside the same project. In 2012, a second team looked at who the marked individuals were. Almost all of them were children or adolescents, and that profile doesn't match the human cases anthropologists use for comparison. It does match something else. When chimpanzee groups clash over territory, the casualties skew young, for the plain reason that young targets are safer to attack. So the second reading is that this is intergroup conflict and the food is a consequence rather than the reason. Neighbors pushed out, territory taken. Both readings work from the same marks on the same bones. Nobody has produced a test that separates a food strategy from a territorial one, and the marks alone can't do it. There's a further complication. A sedimentology study concluded that layer 6 is largely made of material that flowed in. Some of the bone on that reading was dragged in from the slope outside rather than dropped where it lies, which is the same species of argument as the one at the pit. Two sites in one hill, hundreds of thousands of years apart, and the same unresolved question hanging over both. Is this deposit where it was made? So here's why this mountain matters more than the sum of its holes. Almost every other site in this period is a single moment. One cave, one layer, one face, and then a gap of 100,000 years before the next one. You get snapshots hundreds of miles apart and you're asked to draw a line through them. Atapuerca gives you a column instead, stone tools and a face at over 1 million years. A different species and 1,000 pieces of worked stone at around 800,000. The pit at somewhere near 440,000. Then Neanderthals, then farmers, then the Bronze Age in caves on the same hill. One patch of limestone, occupied on and off for more than 1 million years by at least 3 or 4 different kinds of human. That's not a snapshot. That's a sequence, and sequences let you ask questions that snapshots can't hold, which changes how the pit reads. Put it back in the column and the behavior at the bottom of that shaft stops being a bolt from nowhere. Long before it, people on this hill were carrying stone into caves and doing organized, patterned things to bodies. Whatever happened at the shaft happened inside a long habit of using these holes in the ground for purposes that weren't shelter. That doesn't prove anybody carried anything down there. It's context, not evidence, but it does mean the deliberate reading isn't asking you to believe in a miracle. It's asking you to believe in one more chapter of something the mountain already shows. So let's finish honestly and be exact about it. Each explanation for the pit predicts something specific. Here's what each one would have to produce and hasn't. The accident. A trap fills one victim at a time over centuries. So the individuals should not be the same age as each other. Date enough separate bones directly and precisely, and a trap should show a spread of thousands of years. That measurement is beyond current precision at this age. Nobody can currently tell whether these people died in one lifetime or across 50 generations. The flood, moving water sorts things. It aligns long bones with the current, drops heavy pieces first, carries the light ones onward. It also has to start somewhere. What's missing is a source, and a published fabric study of that clay showing the bones lying the way a current leaves them. The carry. If bodies went in whole, then somewhere in that clay there should be pieces of one person still joined or lying together as a unit. Refit enough fragments and you'd see it, and the genomes should show a group, relatives in a population rather than a random sample of a region across centuries. None of that has arrived, not the direct dates, not the fabric study, not the joined bones, not the kinship. 3 explanations, none excluded, and no experiment currently scheduled that would exclude any of them. This may not get settled. Some arguments in this field are simply older than the people having them, which is the useful thing this mountain teaches, and it's worth taking home. Every first in this episode is a claim that somebody wrote down, and every one of them has been shoved since. The best candidate for our last common ancestor with the Neanderthals came back from the proteins as a cousin instead.